standard web development. But if there are things that you want, or things that you're interested, or if you want to speak, let me know, and happy to hear your thoughts. With that, thank you to you, and I'm going to give a shout out to Small, who hosts the space and the food and the drink. If you have any questions about what we do for Slalom, feel free to hunt one of us down, and we'll be happy to talk more. We'll be around after the meetup as well. Kind of give you a little heads up of what's coming down the pipe. We have GraphQL, which I will be doing the first Wednesday in November. And then in December, we are doing a lightning round. So we're looking for 10 folks to do 8-minute talk and 2-minute questions. It can be any subject you want to chat about. If you want to know more, come hunt me down, and we can hear about what you want to talk about. With that, when Jason comes back in, I think we'll get the party started.
Stall.
Stall.
Stall for
time.
Stall. Anybody have any announcements?
Yeah, any announcements?
Anybody part of any cool projects?
Sorry?
What does a lightning talk look like, Sig?
It can look like whatever you want, honestly.
Do you have
So,
an example?
no, that's probably, so I learned something really cool. I had this big problem at work, and I read this blog, and it was fascinating. I think it's the other thing is, I think a lot of people like to go and share their ideas. And Lightning Talk is also a good format for that, because as those of us who've done things like this actually takes a whole lot of preparation. Lightning Talk, you have 8 minutes. So it's really easy. If the audience hates you, they won't. But if you think they'll hate you, you only have to be up there for 8 minutes. And they won't hate you. And so the preparation is pretty easy to put together. And I think what we're looking for is a diverse array of subjects. So we have talked about a pretty wide array of stuff, everything from technical to project management to agile to design. So really the subject's up to you. As I said, just come hunt me down. So that will be December's format. And we're looking at folks to fill it up now. And I'm still stalling.
Yep,
Oh, here it comes.
You're almost good.
Oh, you started?
Yeah,
Hey.
we're stalling for you. Here, put yourself up.
All right, so thank you to Mr. Doherty.
Hey.
Who's going to be doing our talk.
I felt I should put a slalom shirt on just to let everybody know that I actually work here.
Feel like official, right?
I know, feel official. Took a lot to get this t-shirt. So this is a complete introduction to machine learning. If you know stuff about machine learning, you might find parts of this boring. Hopefully not. But I'm just trying to cover like the basics of what is machine learning, why do we do it, what do the different algorithms do. I'm going to do a couple of like live demo-y things, try to explain how certain things work, like convolutional neural networks. So there'll be a few, we'll be focusing mostly on that because everybody likes neural networks because they sound kind of cool and they look like magic when they work. And they don't look like anything when they don't work. But anyway, so machine learning, we've got new ways of actually working that we couldn't do before. And these are things that are very hard to program in any kind of standard language. So things like perception, notifications, what do I need to know, suggestions, recommender kind of systems, automation, predicting things, prevention, situational awareness. So, oops. Those are sort of things that are really hard to code, but these are things that you actually can use machine learning and statistical techniques to be able to achieve these kind of goals in computers in a way that hasn't really been possible before. So some applications for machine learning, I wanted to cover this stuff super early because we want to get into the nerdy code stuff as quickly as we can. Some opportunities, for example, in oil and gas would be to leverage all of the information that's available out in the field. This is some data that one of my customers back in the day collected on paper. It's oil and gas readings from one day for one well. And this company collects it for about 2,500 wells every single day. And they're a small oil and gas company. Buried in that data is a whole bunch of information about efficiency, and they analyze it in Excel every single day. So that's the kind of data that we're talking about collecting and analyzing in oil and gas. And there's a lot of things you can do, like we can use machine learning to automate the data entry. That's all manually re-entered by hand every single day by interns, for reals. We can do prediction with the data, cost reduction, analysis, pattern recognition, production optimization. All those things are possible with machine learning, and oil and gas companies are starting to do this kind of stuff now. In finance applications, you've got forecasting and scenario modeling, working capital optimization, cost management, yada, 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 finance stuff, yay. But essentially, there's a lot of things that we can do in finance because they generate a lot of data as well. Another good example would be log file analysis, something that we do. We dump a lot of data every single day into Elasticsearch. And we sit there with Kibana and we try to analyze the data, but there's a lot of hidden data that's available inside of that data that we don't really do anything with. How do you know someone's hacking your system? So we can do a lot with information and data, but in a lot of cases, it's very hard to program for it in advance. The cost of not doing anything is estimated to be about a 14% revenue loss just through data that's not being used. So there's a lot of opportunity in just being able to analyze data. I swear that's the end of the boring slides. So a brief history of machine learning. This is a nice little timeline. It's actually been around for an awful long time with the idea of an electronic brain, where we actually have the idea of simple gates. Then sort of through the 50s, we have learnable weights and thresholds to be able to act something like a neuron in a brain. We're going to talk a bit more about this in some detail. And then as we kind of go along, eventually, being able to train a collection of neurons that are acting together. The problem was it didn't actually work. And I remember messing around with this stuff in 1992 through 1993. Never actually got anything to work. Then there's a whole bunch of other algorithms that people came up with to solve nonlinear kind of problems and machine learning style kind of problems. Things like support vector machines, which is what that little graph's about. We're going to talk about that a bit more later. And then Geoffrey Hinton comes back again in 2006 with this idea of deep neural networks. And in about 2012, all of a sudden everything changed and everything started to work. So this is the guy, Geoffrey Hinton. And in 2012, for the first time, he actually surpassed statistical techniques for pattern recognition and recognition style tasks. And this was kind of where deep learning was born. And essentially, they got the algorithms to work. I mean, it's the same stuff that if you did this back in the 90s, it works now. And we're going to cover why it works. But basically, we created a new state of the art now for character recognition, image, speech recognition kind of tasks. And Google and Facebook and co kind of noticed a lot. So Geoffrey went to work at Google, as you can tell from that photograph. So this is the guy, and he has just come up with a brand new type of neural network as well. So what changed? Largest thing was wide availability of gaming GPUs. You see a little image in the background there of a NVIDIA graphics card. Turns out machine learning requires an awful lot of computing power, doing an awful lot of vector math. And that's the one thing that computers or gaming GPUs are really, really good at, is calculating a lot of vector math in real time. And so the next big thing was high quality labeled data sets are available. And an important part of machine learning, and we'll go through some examples of this, is you need to have labeled data to do most machine learning tasks. So you might need something like ImageNet has a huge amount of data in it, and it's all labeled data. The next thing was this thing called the vanishing gradient problem, which is about how you go about training a neural network. And that's something that Geoffrey Hinton kind of figured out how to solve in about 2006, 2007, and then finally got all the algorithms to work by about 2012. And the other thing is a whole bunch of new types of machine learning networks became available through that whole period. So we're going to go through each one of these in later slides as we talk about algorithms. Okay, so what are some things we can do with machine learning? You've got object detection and visual recognition. They're pretty straightforward kind of tasks. So the idea is your computer can basically figure out what something is in an image. You can do facial recognition. This was a fun tutorial. The guy that did this actually had to go through and find Waldo in 1,000 training images to be able to produce a neural net that could find Waldo in other training images. That's hard to start with. So labeling that data set took a long, long time. You can also do facial recognition by recognizing parts of faces, which is kind of how iOS does it. So it doesn't do it by trying to do pattern recognition of the entire face. It tries to look at facial features and relationships between facial features, but still uses machine learning to then figure out what something looks like. You can do real-time object tracking. This was another fun little tutorial that was, well, pretty obviously tracking the Millennium Falcon, and we're all nerds. So, I've actually got links, by the way, to the tutorial showing you how to do all of this stuff in the notes. And if you actually go to the notes for this, you'll find links to every one of these. They're pretty cool. Yeah?
Where do we find the notes?
They're in the live video feed for this.
It'll be on the video.
All right, great.
Yep, and we'll post that out. So I've actually just posted all the fun tutorials and all the ones that are actually totally worth your time, and also good intros to get on. Well, I've got all that covered at the end as well, and I'll take you through those. You can do text and handwriting recognition. I'm really bummed. I actually had a live demo for this, and then iOS went to version 12 last week, and Xcode updated, and it can't compile. But I will quickly show you what that kind of looks like if it was running. So basically the idea is you can type in a squiggle and it will automatically recognize it. You can type in names, letters, numbers. It'll go and find what you're drawing in the data. So these are the type of tasks that you can't really code. These are the type of tasks that you're relying on inference algorithms and pattern recognition. And that's where pretty much these kind of networks come into their own. So what's actually happening here is there's a training data set that you create in an app on your phone. You take all those training images, which are labeled data. You throw them into libraries like TensorFlow. And then you can take that library and then run it on a phone. And one of the things I'll cover a few times in this, and you'll hear me say over and over and over again, training a model is really, really hard. Once you have a model that works, you can run it on your phone really, really easily. And iPhone 8s, 9s, and 10s actually have machine learning accelerators on them. And the latest Android phones do as well. And the latest Android phones can run TensorFlow Lite, and Apple has Core ML. So essentially, there's libraries for running machine learning libraries on your phones. They just aren't trained models to run. And so there's quite a lot of opportunity in this to be able to run, create trained models. You've got facial expression recognition. Is somebody sad, happy, whatever, tired, et cetera, et cetera. We're actually going to go through a worked example of how a convolutional neural network works. And then you have time-based recognition tasks. So things like speech recognition. You've got your Alexas and your Pollys. You've got things, I actually looked up Shazam thinking, oh yeah, they'll be using a neural network. They're actually not. It was really interesting how they're recognizing songs. And they're using machine learning to categorize the songs once they're actually recognized, but they're not using machine learning to identify what song it is that's playing, which I thought was kind of interesting. So, steps of machine learning. A large portion of your job is collecting data and labeling data and cleaning data. If you go and do a machine learning experiment from scratch, you'll spend 99% of your time doing that. And anyone that's actually done it before is now laughing. Adam and I were talking about this the other day. So I was trying to train my drone to fly, and I spent a vast majority of my time collecting camera data and labeling left, right, up, down, all that kind of stuff. It's pretty hard. So you spend a lot of time doing that. Labeling data is something it takes a long time. So these are the various steps. Let's talk about each one. So first one is collecting training data. Now, if you're going to use something like most learning algorithms, like all the basic ones that were done before deep learning came along, you didn't need that much data, but the amount of information you need to train an image recognition thing that can find a dog inside of any picture is astounding. So there's a data set called ImageNet, and it has 14 million images in it. 1 million of them have bounding boxes in them already. It categorizes 1,000 different types of data, and within that 1,000 types, there's 21,000 subcategories. So that's a lot of data, and it gives you an idea of like, they have 812,000 images of birds. So we need a lot of data to train these things. And so one of the things we need is data from different angles. So this is a tutorial that is actually up in the notes where a woman trained a neural net to follow a live video feed of a toy. And she only had to label about 100 training images pointing from different angles to be able to get it. But you actually, if you want to train a computer to recognize things, you need lots of different angles. You also need lots of different points of view and different fuzzy ways of looking at the data as well. And so what you can do is this technique called image augmentation, which is what you see on the left there, where you take the same image and you rotate it, you crop it, you stick it through some filters, you blur it. And this can actually give you more training images than you actually have, to give you a bigger data set to be able to train your data on, or train your model on. Labeling your data is painful. If you actually just sat there and drew a bounding box around everything, you do that one image at a time. It takes a long time. An interesting thing is we are training the machines. Every time you fill in one of those capture things, or you go off and identify which one of these images contains cars, you're helping Google go figure out how to image the entire world. So a lot of those recapture kind of tasks are about labeling big data sets. And so we are all guinea pigs training the machines. We said this wasn't about Skynet, but The next part is data exploration and cleansing. There's a thing that I'm going to talk about at the very end called the Titanic data set. There's a website called Kaggle. And it has a lot of different competitions you can do in machine learning. And their primary one that they recommend everybody start with is the Titanic disaster. So you get a data set with 891 bits of information telling you who lived and died on the Titanic. And then you have to predict the other 470 from the information you got from the first ones. And a vast majority of your time is spent cleaning the data and analyzing it. There's lots of data missing. There's things that actually have the wrong values in there. You have to organize things into bands like age ranges. Do you just simply put everybody's age raw into the model? Do you organize them into categories and groups? And different models behave differently depending on how you analyze and clean the data. So a lot of the outcome in machine learning is about how you explore and analyze the data. So in here you can see like the average age of people. Where are we? So the mean for the people we have is 29, standard deviation is 14, and actually you can start to see where people fit into age ranges in the Titanic for people that lived or died. So you spend a lot of your time doing that. From there, pretty much you're looking at using Python and R to do everything. And I don't know anyone using R. Does anyone here even know R? Ricky knows R. Pretty much everyone uses Python. Python's fun. I love Python. I'm a total Python fan, as anyone who gets to know me will figure out pretty quickly. And there's two libraries in particular, NumPy and Pandas. NumPy actually makes Python run as fast as a C library when it comes to doing statistical kind of data analysis. And Pandas is a library for manipulating table data very, very efficiently and quickly. So anything you could dream up that you might be able to do by hand in Excel in like 35 steps, Pandas probably has a library for it already. There's a bunch of machine learning frameworks that are now available, so all of us can play with this kind of stuff. TensorFlow is the main one. A tensor is a vector or an array that's in multi-dimensional space. So if you had, for example, some data that was in 4-dimensional space, that would be a tensor. If you had some data that was in 10-dimensional space, that would be a tensor. And so tensors are vectors, and they get represented by, what's the word I'm searching for? Arrays in multi-dimensional space. And that's why pandas is very important, because pandas allows you to manipulate data in multi-dimensional space. Keras is a library in Python that sits on top of TensorFlow that makes TensorFlow super easy to use. So TensorFlow, to use it out of the box, is miserable. If you use Keras, you can basically build a neural network in 10 lines of code. And if I had my Jupyter Notebook running, I could probably show you that interactively, but that is one that's totally worth messing around with. The other one is scikit-learn. Scikit-learn is another library that does basically everything other than neural networks really, really, really well. Things like random forest support vector machines, and we'll cover those algorithms in a minute. But they're all put together in this thing called Anaconda. There's a library called Anaconda, and if you're interested in machine learning, I'd recommend you all go download that and then start messing around with things like the Titanic competition, and you'll learn a ton. And Anaconda has every single machine learning library you want all in one big package. Gives you everything. And it's super easy to install, except for when it breaks. Jupyter Notebook lets you interactively play around with models and visualize the data as you go, so you can see what's happening at every single step. Then there's Caffe, MXNet, and PyTorch. I've only used Caffe once for training a model for iOS. And the last thing, we already mentioned this, but you can actually have machine learning libraries that are available on phones to run the model. They are not available to train the model. So the basic idea is you pre-train the model, you stick it into a converter, you turn it into a core ML model, and then you can run that on your phone. So training a network is hard. Consuming a trained model at runtime is easy. You will spend most of your time staring at your computer doing this when you are training a model. So what you do is you take all that nice data that you cleaned and you labeled, and then you stick it in a big bin and you give it to an algorithm and you say, all right, algorithm, I want you to go and learn the optimum weights to run my algorithm to give me the best result. Go. And it runs lots of iterations over time, and I'll show you that working in a second, and eventually it finishes. So for example, on the handwriting data set for character recognition, to run it on that Mac took 22 minutes. When I ran it on my GPU, it was a GTX 1080 NVIDIA card, took 2.5 minutes. So it's a 10-fold increase with just one GPU. So the faster the GPU you can get, the better off you are. Or you could get a little extreme and run 8 or 10 GPUs. People really do this stuff. If you have more money than sense, you can run it in the cloud. That works for small amounts of data and very quick kind of things. But it's very expensive to run these models interactively, paying Amazon, as I found out the hard way when I got the bill. So you can run them. It's totally worth doing, but if you're going to do more than a few of them, it's worth just buying a GPU. You don't need a fancy one. You can spend a few $100s and that'll be fine. Anything that's good for Bitcoin mining tends to be pretty good for doing this kind of work as well. It's the same kind of computations. So, some algorithms. They generally fall into supervised, unsupervised, and reinforcement learning. So a supervised algorithm was where we have a labeled data set like we saw before, lots of little toys with little bounding boxes around them or things saying, hey, this is a dog, this image contains a cat. Then we have unsupervised models where the machine tries to figure out what the output is without actually us giving it any guidance whatsoever. They're less common, they do exist. We're not going to cover them today, but they are out there. And the last one is reinforcement learning. And this one's kind of cool, and we'll actually cover this in a bit more detail. So let's cover some of the older, simpler ones. We've got things like logistic regression. Is this a pizza or a hamburger? And essentially what you're trying to do is solve a math puzzle. And you're trying to get the computer to solve the math puzzle for you, which is, here's my sample data set. The green line is kind of, our rough ideal. And we're trying to get the machine to automatically find that pattern in the data. So in the one on the left, you've got what's called underfitting, which is our model isn't a very good predictor of the data. In the middle one, the model's a relatively good predictor of the data. Let's see if my little, hang on, see if my little thingy works here. There it is. Hey. So in that middle one, you can actually see that we mostly get the classification right, but we've got a couple that are wrong. And on the right-hand side, yeah, we got the right answer, but we kind of really bent reality to do it. And so that's not a very good model for predicting the future because we've overfit to the data. So we'll get the right answer for that exact data set, but if we had to generalize it in the future to actually use it on a data set we haven't seen before, that overfit model isn't going to work very well. Whereas the model in the middle mostly gets it right. So what you're really doing is balancing the error level to try to get the minimum amount of error without overfitting the data. And that's the game you're trying to play with machine learning. Sometimes the solution to the puzzle is not in 2D. Sometimes the solution to the puzzle is actually in 3D space. And this is why TensorFlow and all of those libraries operate on multi-dimensional vectors. Because you actually, if you looked at that same puzzle from the top, there is no pattern. When you look at it in 3D, obliquely, there is a pattern in the data. And so the solution isn't always in the number of dimensions that you're looking at. And this is where math gets fun. So there's another library called a support vector machine. And the support vector machine is basically trying to find the maximum way to group things into different categories. And once again, that actually happens in multi-dimensional space. So you take something where on the left here, we have our input space where there isn't really a nice, neat pattern, but when you actually look at it in multiple dimensions, there's a great plane that actually will allow you to dissect the data into two different categories. You just have to think in 3D. Now, it's easy enough for us to picture 3D. TensorFlow and these libraries will work in 4D, 7D, 24D, 96D, lots of Ds. There's also another algorithm called k-nearest neighbors. It works by basically organizing data by the strength of its relationships to its nearby neighbors. And sometimes this algorithm will give you a fantastic answer, way better than deep learning algorithms might give you. There's other algorithms like naive Bayes. You'll hear about this one where I'm trying to classify things into different categories. So on the left, you can actually see the septal length and width of the flower septals. And then on the right-hand side, it's been sort of visualized into 3D space. And this is something that naive Bayes can do, is do multi-category categorization. Often, it does really well at it. Sometimes it sucks at it. And a lot of the experiments with machine learning are about trying different algorithms out. I'm going to get my Jupyter notebook for the Titanic competition and share it to everybody as part of this. And in there, I've got me trying out like 24 different algorithms to see which one gives me the best answer. And it's not a neural network that gave me the best answer either. That was about the fourth best answer. So we have another thing called a decision tree. That's basic tree logic, if then else. And so the basic idea would be something like, are my parents visiting? Yes, we're going to go to the cinema. Are my parents visiting? No. Is it sunny? I'm going to go play tennis. That's the basic idea behind a decision tree, and that's something you could code in code. But what we do with a decision tree often is we try to find the tree that best predicts the data, given the way the data actually is, without us coding it in advance. So we actually get the computer to train itself on how to split the data into these nice little trees. And there's a technique called, I don't know the name of the technique, but anyway, it basically splits the data in a way that ends up with the most predictive leaves of the tree using this factor called the Gini index, which splits the data evenly amongst the different nodes in the data set. So, I'm going to cover two algorithms in more detail. The first one is random forests. A random forest basically is what's called an ensemble method. And what it does is it takes input features like fluffy tail, floppy ears, and furry, and then it runs it through multiple trees. So what you do is you say, okay, scikit-learn, I want you to build me 4 trees with a maximum depth of 4, and I want you to basically organize that data randomly in those different trees to come up with trees that probably will predict the right data, but no two trees are the same. Then what you do is you basically look at what the prediction was from each of the different trees. Then what you do is you run that through a majority vote, and it's a fluffy bunny. So the idea is that multiple algorithms will actually vote on what the result is. And I actually got the best results analyzing the Titanic data set using a random forest. So that was kind of my best outcome there. Now I'm going to talk about convolutional neural networks. These are the ones that are basically voodoo until you sort of get the hang of them. And hopefully I can give you a visualization today of how they actually work so you can get an idea of what a convolutional neural network does. So convolutional neural nets and neural nets in general are trying to simulate human neurons. So you have the idea of a neuron that has a few different inputs that have a weight on them. Those weights are then summed up, and then they get run through some kind of activation function that tries to figure out, do I send a signal along to the next neuron or not? And so what we basically have is a few input neurons, and then we put some data into a hidden layer, and then that goes to an output neuron. The difference between a simple neural network and a deep neural network is pretty much just the number of hidden layers. There's no actual definition of the number of hidden layers to make a deep neural network, but it's probably anything more than 2 gives you a deep neural network. And as you can see, there's a lot of different relationships. So how well will I do at this presentation today? Goes on how well prepared I am and how much I slept the night before. And I did not sleep much last night. So what we're going to figure out is, what are the optimum values of W1 through W9 to predict that outcome of how well am I going to do today? So essentially, I can take my preparation level and my sleep on a scale of 0 to 100, and then figure out how well did I do. And I need a big enough data set for that. And I'm going to take that data set and try to train it to get me the optimum values of all of those numbers. Turns out that if you try to brute force it, that is 1.2 quadrillion combinations. That's a lot of data. You would never actually be able to figure that out. And so that's why they came up with a technique called backpropagation to be able to minimize the error levels of the outcome by interactively adjusting all the different levels by going forwards and backwards through this network. And I've got some links to videos that explain this in 5 minutes and 10 minutes. We just don't have the time to cover it today. You'll find it in the notes, but it'll actually show you this visually on how this kind of training works on training a network. But I do have one visualization for this. But the idea is that you want to minimize the error level at each step. And so you basically feed the error level back, and then there's an algorithm for feeding it forwards. There's lots of calculus involved. And all the math's explained in some videos that you can watch after the talk. So there's an idea of a thing called a convolutional neural network. And convolutional neural networks are often used in image recognition tasks. So I'm going to start off with a hand-drawn 32 by 32 pixel character. And what I'm going to basically do is turn that into a number of pixel values from 0 to 255, depending on how dark that particular pixel is. I'm then going to take that data and run it through a bunch of different matrix operations to produce filtered versions of the output. So some of those output images are going to be things that show me the edges, things that show me like edge detection, background detection, light and dark. And so what we've got is different features for taking that same image and coming up with a convolved version of it. It's like Photoshop filters. If you actually went into Photoshop and actually ran most filters, those are just convolutions and then matrix operations under the hood. So what you're basically doing is taking this data set and you're taking the pixels that are in the pink box over there and you are running them through matrix transformations. That's all you're doing to come up with a different version of the image. So what you end up with when you take these numbers and then you convolve them is you end up with all these different representations for the image. We then take that and we downsample it, so we have less data to work with, because it turns out we don't need a lot of data to make these algorithms work when you get down the very, very bottom. And then we basically repeat and rinse. We run it through convolutions again, and then we downsample it again. And this might seem like a whole pile of garbage, but buried in those little dots down the bottom is information that can be inferred from the previous layers. What we then do is send those simplified features to the inputs of a neural network. So we've got a couple of input nodes, a few hidden layers, and a couple of output nodes that say, hey, I'm a 1, I'm a 2, I'm a 3, and that's how you get the answer. So the computer learns through trial and error minimization which convolutions to use, which numbers to use in these matrix transformations, and also when passing things through the neural network, what are the optimum weights? So when you run the model, you're actually running it through matrix transformation, downsampling, matrix, downsampling, run it through a couple of input layers, a few hidden layers, and an output layer. And then you run that 60,000 times to minimize the error, and you can start to predict the data. So here's an example. This is a super cool tool if I can figure out how to get my screen to run it. Where is my mouse gone? Where is the mouse? Is it up there?
If you shake it, it shows up, doesn't it?
That's a good question. I'm seeing it on this computer. I'm not seeing it on that one. Let's try this. Try mirroring displays. Near enough. There we go. This is going to be really hard to see. Can you guys see this, or do you want me to try to make it bigger?
There we go. That's good.
Are we good? All right, cool. So on the left here, I can interactively draw a number. So I can basically interactively draw a 4. And you can see how each layer feeds into the layer above it. And what I can actually do, this is a super cool tool, you can actually go through each pixel and see where it was sourced from the previous layer. Okay, and then I can go to the next layer, and you can see where that was sourced from. And I can go to this layer and see where these ones are sourced from. So basically, it's like convolution, downsample, convolution of multiple images, downsample, and then it gets turned into a 1D array, which is the input to the input node to the neural network layer. And then it goes to a hidden layer, which is this puppy. And then it goes to the output layer, which is, hey, it's a 4. And so you can see which pixels or which nodes of the previous layer most contributed to the answer that it's a 4. And just to prove that this actually really works, I'm going to go draw an 8. And there it is, predicted that it was an 8.
What's this website called?
It's in the notes, and there's a link, and I can give you this presentation at the end as well.
Can you draw a non-number?
A 9? Sure. A non-number?
Yeah, it's like an X.
Yeah, it will predict something between 1 and 10, because that's the way the model's set up. So it's going to say a 4. So it looks the closest to a 4. Pretty good guess. Yeah, and the demo I wish I could run on my phone would do gesture recognition on a phone. You could type in anything you wanted and it would work. It was great. So it's the same idea as this. It's basically the same demo. It won't work with that because it was trained on data. It all depends on how you trained your model. So if you trained it on the MNIST data set, which that model was trained on, it's a whole bunch of characters at different angles. But yeah, you do have to take rotation into account. There's a type of network called capsule networks that Geoffrey Hinton came up with. Turns out it's pretty easy to spoof a convolutional neural network. So you can take a nose and a couple of eyes and sort of move them all around. And the neural network might still identify it as a person, even though it looks kind of weirdo, like a Picasso, yeah. The capsule networks respect the relationships between features at every angle. So you can take a face that's like super side on, and it'll still figure out how to re-rotate that into a neutral space. It's pretty cool. This is a new little tool from TensorFlow, the TensorFlow playground, and it actually shows you a model training in real time. So over here, you can see the number of epochs that it's been trained over. That's the number of iterations it's working through to try to figure out how to find the best fit over here for the data set. And so what you can see is how the input nodes feed into the hidden neurons that come to the output nodes that then organize the data. And so what's cool about this tool is I can come in here and say, all right, I want to have more hidden layers, and I want to have more layers in here and a couple more layers in here, and then I can try it out. And now it's going to try to fit my data using that model. Might be faster, but it also might not be better, and that's the interesting thing with neural networks. What's faster doesn't necessarily give you the best answer because you can overfit the data sometimes as well. That's something we talked about before. Overfitting is really easy to do with a neural net. So it'll work on this data set, but when it goes to work on a data set it's never seen before, it'll get the wrong answer. So you've got to be careful about overfitting data. All right. So.
How do you know when you're overfeeding it then?
You basically do that by taking the data set that you get, and the way I usually do it is just take 10% of the data. So if I've got a data set of 1,000 images, I'll take 100 of them, and I'll call that the validation data set. And I take the other 900, and I train my model on that 900. And then when I'm done, I run the model on the remaining 100 that it's never seen before to see if I get the right answer. And so you basically split the data set into a training set and a test data set. And that's how you do it. You basically have to validate on data you've never seen before. What you can do, which is kind of cool, is run multiple different models and then get the computer to figure out what's the optimum number of parameters for you. So there's a thing called hyperparameters, which is things like the number of neurons, the number of inputs, the number of layers, how many epochs to run, what algorithms you use to do the optimization functions. You can change the optimization functions midway through training. A lot of people do that these days. Some optimization routines are very, very fast but don't get the right answer. The one that gets the right answer is glacially slow. Turns out you can train it on the fast one up to a point, and then you can switch to the slow one to finish it off to get you an even better answer. All of that setup is called hyperparameter optimization, where you're trying to find what's the best settings to use. And so what you can do is you take your training set, your test set, and you can run it through the TensorFlow, or Keras has some tools in there, and scikit-learn has tools in there that will basically run your data set and train it hundreds of times, trying out different hyperparameters to search for the best hyperparameters. It's called a grid search, and it'll look for the best values to use to configure your network. So there's an art to machine learning, which is picking the right models and picking the right number of layers. But turns out the machines can be trained to train themselves on figuring out what the right numbers are. That was a good question, thank you. All right. All right, we're good.
I think we have one more question.
Yep.
Kind of a follow-on. Can you talk about some of the pros and cons of using regressions for determining accuracy?
Doing regressions on the original data set for a convolutional neural net, or for?
Sure. Doing regressions on the resultant, the results of the data set to determine accuracy.
I mean, I've never done it. I usually just do it by having an accuracy value for the prediction, and I just keep running it till I can find the right hyperparameters to use. I don't try to do any kind of regression analysis on it. I mean, I'm not a deep learning super nerd. I just dabble in this stuff.
Okay.
Same
here. I saw another presentation about regressions.
Yeah, I've never got into that. I mean, I've vaguely heard of it, but no, not really. Mostly what I do is I just run a model a whole bunch of times, and I just write down my results. One thing, if you do get into this and start messing around with something like doing the Titanic Kaggle competition, write down everything you did. Because you'll do something, and it'll be good, and you'll try to tweak something else, and you make it way worse. And you won't remember what you did. And then you won't be able to remember how to get back to where you were. And I did that a couple of times. So keep a little journal about what you were doing. That's how I've done it, but for me, it's just dabbling. I'm not trying to do data science kind of stuff. To sort of visualize what that looks like, though, and running that through multiple different layers, you're basically taking an input image, you're turning it into 3 different layers, you're downsampling it, you're basically turning it into different layers, you're running different features on it, convolutions. Rel use a thing called an activation function that basically says, do I pass the data along to the next step, yada, yada, yada. You'll see these diagrams a lot in machine learning showing how an algorithm works. Now, there's a lot of art in this, This is the diagram for Inception v4, which is currently, I believe, the best image classification algorithm in the world. And that is the number of steps they go through to come up with the right answer. And I can't begin to fathom how they came up with this, but yeah, this is their version 4 of it. And then that Jeffrey Hinton guy has a new version based on a technology called capsule networks that's supposed to be able to beat this thing. And that was trained on the ImageNet data set. So imagine the amount of processing power it takes to run all those calculations to optimize all of the hyperparameters for them, find the right number of nodes to use at every layer. Because every time you see one of these things here that's like fully connected, that's a neural network. And so all of this stuff has to happen before it goes down to this fully connected network and the last part of the training happens, yada, yada, yada. All of that stuff has to run on a GPU and do all those calculations to come up with the optimum values to use. The nice thing is the wonderful people that built this make the trained model available for you. So you can just download this and run it on your phone. Not all of them. ImageNet's too big. There's a version of it called MobileNet that'll run on your phone. The actual model itself is too big to run on most phones. The other thing you can do is you can take a pre-trained model that's already got the right values, and then you can take it, you can give it a new data set it's never seen before, and what you do is you freeze all the middle layers. So you basically take the Inception model, you take all these middle layers and you'd freeze them, and then you'd take something like these input layers at the top, and then you would give them new data they've never seen before. And that actually works out in a lot of cases to allow you to recognize images that that original algorithm was never trained on. So it's called transfer learning. You can take a pre-trained model and transfer its knowledge of how to recognize things onto new and novel things it's never seen before. Some other key algorithms, just because they're kind of fun. There's one called recurrent neural networks and another one called LSTM, or long short-term memory networks. Those are good for recognizing time series data and doing reinforcement learning, because they can actually have different nodes that feed back on themselves, and you can also have nodes that feed forwards and backwards through time to analyze time series data. I've tried to get one of these to train it on music and failed horribly, so still haven't figured out how to do it. Then there's this thing called generative adversarial networks. So we have this idea of I'm basically going to get a network, and I'm going to train it by having a neural network on the left and a neural network on the right. Or I'm going to get two neural networks, and they're going to basically play a game. Neural network 1 is going to take a picture of money and try to figure out whether it's actually money or not. And then neural network 2 is going to basically take a bunch of numbers, or take a number, and try to basically produce a picture. Okay, so that's the game they're going to play. Neural network 1 is going to produce pictures of money, counterfeit money, and neural network 2 is going to try to recognize counterfeit money. So, first go isn't very good, but unfortunately, our neural network isn't very smart right now, so yeah, it just thinks it's money. So then what we basically do is we say, no, we're going to retrain the network, we're going to go through another iteration, and we're going to take our fake money, and we're going to say, nope, not real money. And so the other network's going to adjust, and essentially what you have is two networks fighting themselves out for the best answer. I've seen some really good uses of this. One is somebody was producing levels of Donkey Kong, or no, it was Mario Brothers, where one algorithm was producing levels and the other algorithm was producing somebody that could run through the levels. And so they had an automated Mario that could beat most Mario Brothers games, but they also had a Mario Brothers level generator that could make levels that Mario couldn't win. So it was kind of cool. They could actually have the two different things fighting each other out. So repeat that 5,000 or 100,000 times and you get Skynet. Not really. And so that's basically it for the talk. That's really just, here's what machine learning is all about. The thing that I would recommend you all do is this thing, which is the Titanic disaster. What you get is the information on 891 people, whether they survived, their name, sex, age, cabin, passenger, class, siblings, number of parents, children, ticket, port of embarkment. The data set is not complete. There's lots of holes in it. And basically what Kaggle give you, this is on kaggle.com, what they give you is the training data set, and then what you have to do is train your model, and then what they give you is the prediction data set, and you have to predict whether people lived or died. You upload that, and they say, yep, you came 7,000th, as I found out the first time I did it. The best I've ever been able to get to is 2,167th in the leaderboard out of 11,000. So I got an accuracy rating of 0.83 using a random forest. That was the best I was able to do. And I tried out like 20 different algorithms, and I'll make my Jupyter Notebook for that available. There's a guy who's written an incredible Jupyter Notebook. Jupyter Notebook's like this interactive Python tool that lets you basically run a bit of Python, then see the result, run a bit of Python, then see the result, and it stores all the results. I was going to show this to you, but my server crashed like this afternoon, so I can't, sorry. But basically, you will take that Anaconda thing I talked about before, install it on your machine, you type Jupyter Notebook in, and then you can start training your own models. I've got a link to a guy that explains in exquisite detail how to approach a machine learning task from scratch, and then how to work with things like NumPy and how to work with things like pandas. So, bunch of resources. These are all posted up in the channel. There's the Where's Waldo toy data detector, the Millennium Falcon tracking, the link to the handwriting recognitions up there as well. The pictures of money, I didn't create them, stole them, thought they were funny. Machine learning is fun, fantastic website that's got like 9-part series, I think, or 7-part series or something on machine learning with tons of introductory stuff. The Titanic Kaggle kernel. There's this thing on Kaggle. There's this thing called a kernel, which is a solution to the problem. So somebody has posted a solution to how to approach solving the Titanic problem, but it is by far and away the best explanation I've ever read on here's how to approach a machine learning problem from scratch. Some YouTube channels that are worth your time if you want to understand this stuff. Suraj Raval is batshit crazy. When you've seen his videos, you will understand. But he covers machine learning topics in 5 to 10 minutes. He talks at 1,000,000 miles an hour. His belief is that most people speed up their YouTube videos by a factor of 3, so he's going to just talk that fast. He's super animated. He sings. I'm just warning you. It's fun. I like it. You might not. It might not be your jam. I think he's great. Backpropagation in 5 minutes is one of his videos. He actually explains how backpropagation training of neural networks works visually. Pretty cool. This other one, Fun and Easy Machine Learning course in Python and Keras. That's the link to the course. It's available for free on YouTube. It's also on Udemy. Awesome series of lectures with a guy that hand draws everything, but he does fantastic explanations of every algorithm, shows you how to use them. The thing I like about Suraj Raval is he does interactive coding on the screen, so you can sort of follow along if you sort of hit pause all the time, because he talks so fast. These are the recommendations that I have, and I'll make this presentation available as well. That's about it. Thank you. So, any questions? I probably can't answer them. Yeah?
So to be able to use a neural network and to be able to verify that it's running correctly in whatever you're building, about how much math do you need to know?
If you use Keras, none. Pretty close to none. I would suggest you look at this Suraj Raval guy's things, and machine learning is fun. Actually, even the Titanic Kaggle kernel, what you're mostly doing is a bit of Python programming, statistics, but you don't have to know the math of the statistics. There's libraries for doing all that stuff. That's why NumPy, Pandas, Keras. If you know NumPy, Pandas, and Keras, you can pretty much do any machine learning, any neural network task. And if you want to experiment with things like random forest and support vector machines, then scikit-learn. And they're super easy. Like 5 lines of code, you can set up a neural net. It's like, I want a neural net, I want 7 neurons. I want 4 layers, 7 neurons each go. And it just does it. You don't have to think. It's awesome. If you had to set that up in TensorFlow, it's this miserable thing of linking all these layers together, and Keras just puts a nice wrapper around that for you. So they make it super simple. All of my experiments that I've done with this, it's usually been like 100 lines of Python or less, and no math to speak of. You could code a neural network from scratch. I don't know why you'd do it, but you could do it.
Well, I can actually answer that. I did my master's in machine learning specifically. The math came in when you start tweaking the decay rates of back propagation.
Yep.
Just don't do that. You're just straight up not going to be better than what TensorFlow gives you anyways, unless you need to go write a paper so you can graduate. That's accepted news.
I didn't think about that aspect. Yeah, that's true.
Yeah,
so if you want to invent something new, like that Jeffrey Hinton guy came up with these things called capsule networks, and I've read the paper 3 times, and it still just boggles my mind, and I have no idea what he's talking about, really. Like, I know vaguely how it works, because somebody else wrote a paper visualizing what he did, but if I hadn't seen the little visualization, I wouldn't have been able to figure out from the math. It was just way over my head. So you don't have to know the math to figure out how to make this stuff work, because this gets into pretty advanced calculus. This video on backpropagation in 5 minutes, this guy actually shows you, it's Suraj Raval, shows you a visualization of actually figuring out how to optimize just one node using calculus and how to visualize what's actually happening. And it's, once you see that visualization, I mean, I can run the video now if you guys want to see it, but it's kind of cool. Actually, I'll run it while I'm talking, because then you can just see it. Oops, no, I'm running presentation mode still. So yeah, a lot of that math you don't need to know. And yeah, Ricky's right. There was another question while I'm cutting and pasting a URL.
Yeah, does the same go for statistics that you need to know? So libraries you can avoid some of that.
Have you thought about exploring
What kind of
machine
statistics?
Hang on, I'm just exploring my Udemy. I'm going to take the online machine learning course.
It's Suraj, and today
Oh, wow.
5 minutes. Gradient descent is a popular optimization technique and can be used in many different types of machine learning models. It's used to optimize or improve the accuracy of our model's predictions. One implementation of it that is particularly popular is for neural networks. A neural network is a learning model that can make predictions. We give it some input data. The X values represent the input, and the Y values represent the expected output labels. Our network's job is to learn this mapping so that given some arbitrary input, it can correctly predict its output label. So our 3-layer neural network will first have an input layer. Each neuron represents a different row from our input data. Then it has a hidden layer. Data will flow in one direction from our input layer to our output. And the way it does this is by having weights that connect each neuron in one layer to every neuron in the next layer. We can initialize these weights as matrices with random values to start off with. We'll multiply each row of the input by each column of our weight matrix. The resulting values from this operation results in our hidden neuron values. We'll take each of those values and convert them to a probability value. That is a value between 0 and 1 by applying an activation function to it. The type we'll use in this example is a sigmoid. So each neuron receives a set of inputs, performs a dot product, and then applies an activation function to it. We'll just repeat this same process again to calculate the output prediction. We compute the dot product of the hidden layer neurons and the next weight matrix between the hidden layer and the output layer. Then we once again apply our activation function to it. This resulting value is our prediction, and this process that we just completed is called forward propagation. If we compare this to our expected output, we'll see that our prediction is incorrect. We want to find the absolute best weight values that, given any input, they would help calculate the correct output. To do this, we'll first want to calculate an error value. We want to minimize this error. If we were to create a simple graph of the error value versus some random weight from our network, it would look like this. Too small a weight value and our error is high, but too big and our error becomes high again. We want an optimal value for each weight in our network where our error is smallest. Starting at some random weight value, we want to take a step in the direction towards the minimum error. This direction is the opposite to the gradient. If we take many steps descending down the gradient, eventually the weight will find the minimum of the error. We call this process gradient descent. So how do we do this? Well, we'll need to use calculus. Let's do a little refresher on 3 terms from calculus.
And this is about where we all tune out. So, to answer your question, that's what it's doing. If you wanted to write a neural network from scratch, you need to watch the rest of this video. If you were to use Keras, it does it for you. And that's the whole point. If you use a library like Keras, you don't need to know how to do this stuff. You just say, I want to have a neural network, 5 layers, solve, go, and it'll give you the answer. And so it depends on how deep you want to get into this stuff. So that's kind of answered your question, because you can see this is just going to go downhill from here. Good video to watch at home, the rest of it. It's true, exactly. Yes?
So coming from ML kit land, if I'm looking for a monarch butterfly and feed it an image and it comes back and says, I'm 87%, sure. This is where I'm deriving that 13% right there. Is that correct?
Kind of. So when a machine learning algorithm makes a prediction for multiple categories, each one of the output categories is like a node on the output layer. So to go back to, where is it? My little prediction of whether or not I'm going to do this presentation well or not. I think that was down here somewhere. Where are you? There we go. So essentially what you've got is, here's my input nodes and my output nodes. If I have multiple output nodes, remember that visualization of the number 8? There's going to be multiple output nodes, and each one of those is going to have a probability that it's the right answer. So every node gets a probability, and you just pick the one that has the highest probability. So what your answer was giving you was basically telling you that this little yellow circle here was 87%, and this little circle here was 50%, and this little circle was 15%. So it's not actually giving you the weights for an individual node or connection between the nodes. It's giving you the probability that that node has the right answer. Does that make sense?
It does.
Cool. Yeah?
Let's say I'm interested in ML and I want to bring it to work. What are some common problems that I could solve, or that ML can help me solve at work to improve law?
I mean, those oil and gas ones, it depends on your use case. All the things I've been looking at are musical or computer vision because I'm interested in that stuff. For work, I don't know. I mean, I thought of this last night. I was at a Lenny Kravitz concert last night, and Lenny Kravitz is like walking around the stage. About halfway through the show, I noticed one of the follow spots was following him across the stage flawlessly the whole night. And there's no human there doing it. And I was looking at the guy at the lighting desk, and he wasn't touching anything. So then I noticed there's a couple of cameras on the side, different angles, that have got visibility of him on the stage. So they pretty much, and I looked it up and I found the people that do this. That would be a good example of a real life application of machine learning. There's things like the parking trolls. I hope nobody hears one. Driving around Denver, they actually photograph every single license plate, do character recognition of it. They know where you are. They can look at your license plate to see if you've moved your car, so you can't just keep feeding the meter all day, which is not fun, whatever. Anyway, there's lots of practical uses of this kind of stuff. Yeah, it's one immediate use I can think of, but it's from my current customer, and I can't say a thing. So, what are you going to do? But I think it depends on the use case. And there's a lot of things that are buried in log data that you could do. There's a lot of things that are buried in data sets for oil and gas. It just depends on how much data you've got to feed into it and whether it's labeled data or not. Yeah. Yep.
So let's say I work for the Denver Parking Authority and they don't
Sorry.
have this machine learning set up implemented. Is there a way to eyeball how many pictures of license plates I would need in order to train something? Like, how do I guesstimate my needed data set?
I trained a handwriting recognition thingy on about 100 images. That toy detector was originally trained on 130. The guy that did the Millennium Falcon trained it on, I think, like 500 images, and then later went back and figured out that 137 would have been enough. It just depends on how homogeneous your data is and how many other things might confuse the algorithm and how much angles and things are involved and all that kind of stuff. And how much you can do data augmentation to augment your data set. There's also the concept of bias in the input data set where, say you're trying to predict whether or not people are going through airport security with a knife in their bag, because sure. If only 1% of people walk through with a knife in their bag and 99% of people don't, you have a network that's actually predisposed to not find people with knives in their bag because the input data set wasn't evenly distributed to be able to train the network to find people with knives. So you've got to be careful like what you're trying to train on how you collect your data. Remember before I said collecting of data is the biggest problem and labeling it, not training the network. Training the network's hard, don't get me wrong. There's a lot of art and science to it. But yeah, a lot of your time is spent just collecting and labeling data and cleansing the data before you start. So you can get by with like 100 training images, but if you want to do a real world application, it has to survive the fact that people might have handwritten things written on their license plate and all sorts of crazy stuff. Stickers on their license plates, you know, there could be all sorts of crazy things that are there that'll throw it off. So generally you need larger data sets and labeled ones. And for commercial applications, like for fun applications, which is what I do, I don't have to be that accurate. If I'm 82% accurate, I'm happy. But if I'm going to be giving people parking tickets, I better be 99.999% accurate. So real world applications are a lot harder than, you know, toy applications, which is all I've really done. Mm-hmm.
I have a question kind of piggybacking off of that a little bit. A long time ago, I actually had an application I was working on where we were using, like we were taking pictures of something and seeing if it recognized a logo. And essentially, a part of what I was doing on that project was also like working a little bit with that and also going in and saying like, oh, here's the whole thing of all the images we captured, which ones are actually the logo, and then like retraining it. How useful is something like that? Like someone going in and like selecting from the list of things that it could be, going back in and like trying to like retrain it to make it better. So I always wondered if I was actually really helping it by giving it those more data points, or almost hurting it by giving it more data.
Yeah, I actually had that happen with the MNIST data set too. I thought, oh yeah, I'll just run this over more epochs and yeah, and I never got a better result. I think at the end of the
I felt like we never got a better result, but like my boss was very insistent that no, go through all those thousands and thousands of images, find the right images, and retrain the data set based on the new images that, you know, because people would take a picture, it would either be the logo or not.
Mm-hmm.
I would go in and see the everything data set and then make it and try to refeed back in the correct responses.
Yeah, I don't, I mean, honestly, I don't know. I haven't done production things. I've just toyed around with this, but I've actually found that the more I try to help past a certain point, it just doesn't get any better. I don't know, on some of the data sets that I've messed around with, I'm not quite sure how some of the people that do better than I do on Kaggle competitions know. I don't know what they're doing. I'm sure some people are cheating. I got to be sure that, because they're getting like 100%, that can't be possible. But you know, people get pretty damn fancy at like cleansing these data sets too. So the best solution I've ever seen to where somebody actually advertised how they did it for the Titanic data set, people are basically finding relationships between family members and chaining them together into family units as groups and then figuring out whether the family unit lived or died. I never would have thought of doing that. Like taking everyone with the last name and then looking at the number of siblings and then correlating them, and then figuring out the family unit survival rate and creating like metadata of the data and then analyzing the metadata. I never would have thought of doing that, not a million years. And they did better than I did. So maybe not feeding more information in, but maybe thinking about the data differently might help. I don't know.
Improving the data quality.
Yeah.
Going with the Titanic thing, one of the things that got a really high result was they created a 3D map of the room numbers and then correlated distance to an escape.
Oh yeah, that's a really good solution. I've never heard of that one. That's awesome.
Perfect freaking sense.
Yeah.
Like the closer you are to a lifeboat, the more likely you are to survive, probably.
But you would add in data that the data set doesn't necessarily have.
It doesn't. It has a room number, but the room number
First class, second class.
Yeah, and no one could do anything with the room number. And there was another one which was like, where did you board? Did you board in Southampton or Queenstown? And then somebody figured out how to correlate that with your ticket number to figure out where you were in the cabin in relation to the other cabins and where you're further away from the doors. So people found like relationships in the data and then used that as predictions and then fed that into models to actually do the predictions. Like people got really, really creative, and stuff that I never would have thought of. I wouldn't have thought of that room number and creating the 3D map. So yeah, to answer your question, like sometimes you just got to think differently about the data. I don't know. I haven't had a lot of luck with just going back through. I just get to a certain point, I'm like, but I'm.
This was also back in like 2011, so
Yeah,
like,
way early days.
yeah.
Cool. Another interesting factoid I took off here, since 2006, every single paper check in the US has been processed with a machine learning algorithm to read your handwriting and check them out off the back. So.
Same thing with post office, all the, they run everything through, like handwritten envelopes.
Yep. So they've got huge data sets to be able to train things on, but yeah. Cool. Well, thank you, everyone. I'm going to have to figure out how to share this in a way that's keeping all the videos. Yeah, the file's like 128 meg, so with all the animations and videos and yeah, and even the PDF was 110. I got to figure out how to make it small. I'll probably put it on a Google slide or something like that. Yep.